Hey physics students, welcome back to another edition of Rapid Review for Honors Physics. Today our topic is continuation of waves, and we're going to focus today on modes of standing waves and the harmonic series. Let's take a look. You might remember that doing experiments with springs on the floor and trying to find V equals F lambda and all that, you notice that you could make different shapes. I'm showing 3 of them here. I'm going to give them a name now. I'm going to call those shapes modes with an M. Likely to lead to possible confusion, modes with an M, not to be confused with nodes with an N. I'll try to be careful in my pronunciation, and hopefully we can depend on context to avoid any further confusion. But we're looking at 3 different modes of standing waves in this picture. Others exist, and we're going to analyze those modes and see what modes are possible. In doing that, we're going to discuss lambda, the wavelength, in relation to L, the length of the medium. So I show on the left side here, I show the length of the medium. I show you that, right? It's the same in all of those pictures. And on the right side here, I'm showing you how lambda relates to the length of the medium in various modes. So taking this one in the middle, which is probably the easiest one, you can see that you get a full lambda, a full wave. Remember, that includes both the down and the up, and that happens to equal 1 length of the medium. Here, I have a wave takes up 2/3 of the medium, right? So the lambda is 2/3 of the length of the medium. And here you have to use your imagination a little bit. You have to take this and extend it out. I'm going to run out of room in my slide. Let me do this one. I'm going to extend this one out. I'm on my left side again, and then back again. And you could see that that is 2L to get to a full wavelength. That's why lambda is 2L in the top example. Okay? So there's always a relationship between the length of the medium and lambda, and if you know one, you could figure out the other. Let's skip ahead. I'm going to zip through a million slides here, and I'm going to just jump to a summary which really says everything we want to know about it. So in the presentation here, we look at 2 different cases. One is the one we've been doing on the floor with springs, where you are kind of stuck with a node on both ends. You shake a little bit, but not a lot. So it's a node with an N, node, and on both ends. And if you do that, you can see on the left side here, the possible shapes you can make are, I'm giving 3, but there's more, right? So you can have L as a half lambda, L is 2/2 lambda, which is lambda, 3/2 lambda, and so on. The pattern goes 1/2, 2/2, 3/2, 4/2, etc. You can go on forever. That is called the harmonic series, and that describes the mathematical solutions to how you can create a standing wave in a medium of length L. If you find that interesting, you will enjoy your studies of differential equations in the future, probably a college course, and you'll find other kinds of examples of mathematical problems that have multiple solutions. And that's an example of one. It's a classic case, right? It's a vibrating kind of a string here, right? So that's all based on something we've done before. But there's also, if I allowed a person to shake the string really broadly and created an antinode. Now I'm on the right side of the picture. If I force an antinode on one end, but I keep it fixed on the other end with a node, the set of solutions are different. You can see in the picture that the shape I'm making in these 3 examples on the right side is different than the shapes you saw on the left side. And the relationships between L and lambda follow a different pattern. Here you can see the pattern, 1/4, 3/4, 5/4. You know where it's going. 7/4 comes up next, and so on. Those are the different modes that are possible if I constrain my problem to having an antinode on one end and a node on the other. Okay? So the solutions, the set of solutions that dictates what kinds of standing waves you can get has to do with the constraints at the end and whether you have antinodes or nodes. This will become really useful when we analyze systems that make sound, which we will get to. Okay, so that is the harmonic series. These names don't matter too much. You should know fundamental, which is the smallest one, and then the others have names of harmonics and first harmonic and second harmonic, and don't worry too much about which harmonics they are. They do have names, you can look them up. We, in our class, we made a simulator. If you had a collection of marshmallows and what do we call them, bamboo skewers for barbecuing, and some duct tape, I kid you not, duct tape, you can make a simulator that looks like the one I'm showing you here. There's duct tape moving through a center line. There's duct tape, and I have a bunch of skewers crossing it, connecting to marshmallows that add mass at the end of the skewers. And that device is something we can use to make standing waves. All you have to do is rotate one end of it. We have a student here on the right side rotating it. You can see that it's COVID era because there's a mask. Anyway, that student's rotating, creating an antinode on one end, and the other student in the red is holding it still, so there's a node at the opposite end of our simulator. And if you look at that, it's exactly what we talked about, the third harmonic for a system that has an antinode and a node on respective ends. Okay? So as predicted, the length is going to be 3/4 lambda. Let's look at another example. Here's a student. Let's see, a student using a small amplitude, so he's effectively creating a node, and we allow a big amplitude on the other side to create an antinode on the right side, and you can see he figured out the frequency he needed to use to create a fifth harmonic. One last example, here's one similar to the springs on the floor, nodes at both ends. You can create a second harmonic of a system that has a node on both ends. I encourage you to try, if you're able to make one of those simulators. They're actually kind of fun to play with, kind of like the springs, and you can learn a lot about wave behavior by having a simulator like that. In fact, I think there's a YouTube thing that shows somebody building something similar. I will try to link to that if I can find it. I'm sure it exists somewhere. Okay? I think that's all I want to say about modes and harmonics today. So let's stop this topic for now. I'm going to move into longitudinal waves in another video. I hope you'll join me for that one. We'll see you then.